is going to present this, and I think it's streaming now. So
awesome.
Yeah.
All right. Yeah. So I have some knowledge here. I hope. So in a zero knowledge proof, after the talk, you wouldn't know anything about my knowledge. However, I hope I can convey something to you, actually. All right. So the goal with this is, well, it's a bunch of philosophical stuff here at the beginning. But in smart contracts, I think everybody knows there are a bunch of high-profile examples where people screwed up and like money got burned big time. So and the question is, what can we do about this? And so there's this idea that code is law. You may personally disagree. However, you should maybe at least be trying to think about, we should at least get it right, even if you disagree with this statement. And so the issue is in the real world, we have all these lawyers, and they like work out all this stuff so that there is really no loophole. And in general, I would say programmers, I think we all have the experience that there is some bug where there really shouldn't have been one. And yeah, programmers are just not the kind of people in general. There are certain programmers that I would trust. But yeah, in general, they maybe should be trusted less. And also, there can also be malicious intent, and it's sometimes possible to hide some vectors really, really well. So if you have access to the source code, you can still find some weird backdoor. And well, as we've seen before in this nice graphical language, it would be much easier to spot a backdoor if you had this diagram, and you kind of know that everything that happens in your execution is somewhere in this diagram. And that might be a good way to avoid backdoors. And so we need tools like those diagrams that let us reason about these kinds of things. And so yeah, that's more of the general idea. And in a very specific sense, we need to formalize, or we wanted to formalize these executions of automata. And so first of all, let's talk about what's a zk-SNARK. I think many of you have heard this term. So there's this fancy definition, let's say, of or expansion of this acronym. I'm not going to talk about what it all means. All these words in there have certain meaning, but in general, the idea is that we have a function that's publicly known and some value. And so you can imagine, for example, f would be like a hash function. And it could be, for example, some function that verifies that when you append blocks to your blockchain, then well everything has gone correctly. That's the classic example maybe in this kind of community. And so what we want to do here is we want to so Fab actually I think Fab came up with these names, Peggy and Victor. We have the situation where we know an X, and we want to prove to somebody else that we know this value X, but without telling him anything about it. And you can imagine here something about, okay, I have this block that I want to append, and I know what kind of transactions happen in the block, but I don't want to tell the public what's actually in the block. I just wanna be sure that that everybody can verify that I can actually append this block. It contains valid transactions, but without revealing what anybody actually did. And so this is this is really what this zero-knowledge system is about. And so if you know about problems in NP, in computer science, then that's a very similar idea where it's somehow you have this x that's maybe very difficult to compute. However, it's very easy to check that it does what you want it to do.
Sorry, what is B?
What is what? B. Booleans. Yes. So talking just about like finite bit strings here. And that's actually important right now. Because how do we get to this thing? How do we encode these kinds of things? And there are actually, if you read about zk-SNARKS, there are a ton of different kinds of pieces of data from which you can get zk-SNARKS. And the one that's maybe the most talked about are these arithmetic circuits. But in our case, because we don't really wanna like add numbers and stuff, we are more want to talk about logic things. We use Boolean circuits, and Boolean circuits are actually nice because they're in some sense the most basic thing that we can generate the snark out of. And so it's actually the most efficient thing we can use, and well, for our purposes, also the most natural one. So that's very nice. And so what we do now is we looked at this for a while, and then we realized, well, Boolean circuits are a category, in fact, a monoidal category. And so we have this nice idris-dt library, which we can use to work with those kinds of things. Yes, and I skipped over the first point. We need to define a bunch of circuits, a bunch of gates to actually wire into our circuits, which the only thing that we really want is we want a bunch of such gates so that every function can actually be expressed as a circuit. And like if you're aware of some computer science, you might know that a NAND gate, for example, is basically all you need. In this categorical setting, you need to provide a bit more because the notion of gate is very slightly different, but that's only a minor technicality. So nothing to worry about here. Yes, and so now how do we do these things actually? Well, we have a finite state machine, which is just a bunch of you can imagine as a graph, right? You have a bunch of states, you have a bunch of arrows that allow you to go between states, and you can also view it as a very simple pattern net if you want to. And so what we want to do is we have a current state. We want to say, oh, now we are in transition X, and now we're in some new state. And so we use a function that does this kind of computation. So we feed it some state that's encoded in n bits. We have m bits for the transition, and then we say, well, is this a correct transition? Yes or no? And if it was a correct transition, please give me the new thing. And if it was an incorrect transition, we don't even care about what comes out here. And what we do is we take our state machine and turn it into such a circuit. All right. Right. So and the nice thing is, if we do this in idris-ct, we can actually prove that the circuit that we generate implements the same code as this checking function that verifies if a transaction is actually real. And so this uses a bunch of nice properties about functors, and actually it uses the category of idris types and functions. So this is a very nice thing where we can be sure. If you imagine we have the circuit and imagine that it has like if you imagine in this case this n and m. If the circuit is if the state machine is large, you can imagine like a number of thousands or something on there, and then the circuits are insanely large. So so you would want to actually have a verification that the circuit does what you want, right? Because even if we have this nice graphical editor, you don't want to have 10,000 wires hanging around and checking that everything goes where it's supposed to be. Yeah, and then from there on we can generate the zk-SNARK. There's this nice library called libsnark that basically does this more or less for free. And we can then run it on Ethereum. And as a nice bonus, we get tooling for working with Boolean circuits, which is always nice because maybe you want to do some hardware stuff, or Boolean circuits have tons of applications. So yeah, that's pretty much it. You can find our paper on the archive. The paper is much more in depth and covers a bunch of things that I haven't really talked about. For example, how to do this not for a fixed state machine, but where you can allow basically specifying the state machine after the smart contract has been deployed. But yeah, there's a bunch more to actually talk about in that scenario. Yeah, I think. Any questions? Yeah.
So I can play with it a bit, and that would be fun. But like, what does it look like? Like the higher the complexity of the Boolean, like 200 nodes and above, like you get into these situations where like it's self-cyclical, right? Like it can.
Yes.
How do I? Does it tell me? What does that look like? Is it like a 50-50 representation of a yes or a no? Or?
You mean in the code, or?
Yeah. So what does it look like in the clip? Like, what does it look like for me to know when I've created something where it's going to be bistable?
So the circuit itself, the category of Boolean circuits is actually, we do this using free monoidal categories, which is precisely what Fab mentioned, where we have this quotient issue, which is kind of fun. And so we actually, the circuit does only have wires basically pointing downwards. So you don't have any circles in there, for example. So that's not an issue there. So you can't do memory, for example, in there. And that's actually that matches what you can do in these zk-SNARKs. You cannot put any sort of circuit in there. You have to have a circuit that kind of that cannot feed back into itself, basically.
Let's thank the speaker again.
Yes, sir.